Hi, welcome back to the next video in the IB Math AA higher level series. Today, we'll be looking at differential equations. So differential equations are just equations with derivatives. So for example, this is a differential equation because it has a derivative right over here. This is a second order differential equation because there's a derivative of the second order, there's a second order derivative. So it's the derivative of a derivative, and it also has a first order here, but this is primarily a second order differential equation. So we'll be just looking at some methods to solve these. So first is Euler's method. This is a numerical way to solve it, and it's just an approximation. It's not an actual solution. So we recursively approximate solutions here, and it's almost always done entirely on the calculator. So to do this, you first write down recursive equations in the form yn plus 1 equals yn plus h times f of x comma xn comma yn, and xn plus 1 equals xn plus h. So we will see later that h is the step size, so that's always given in the question in some way, shape, or form. And all you need to do is just sort of fill these in, type them directly into the recursion formula in the recursion function of your calculator, and just make sure to fill in any initial conditions, and you can solve it. I think this is best demonstrated with an example, which we'll do at the very end of the video as part of the exam question. So I'll come back to the slide once we go do that. So to improve Euler's method, there's just one way, and that's decreasing step size. So if you look here, you can split this curve up and simulate it in different ways. So for instance, I could try and simulate it with a straight line if I took some massive steps like this. Or if I took smaller steps and made straight lines, I could simulate this curve a little bit better. So as you can see, these smaller steps are much better at simulating the curve than this straight line with a massive step. So yeah, the only way to improve Euler's method is to decrease the step size. Now let's look at the easiest type of differential equation to solve, separable differential equations. So that's in the form dy by dx equals g of x times h of y. So you have a y term and an x term multiplied with each other. So first you rearrange it into this form, 1 over h of y times dy by dx is g of x. Then you split the dx to the other side, so you treat dy by dx as a fraction and multiply both sides by dx in order to get 1 over h of y dy is equal to g of x dx. And then you integrate both sides, so the left side you integrate with respect to y and the right side with respect to x. And then, of course, you get a plus c. You only need to write 1 plus c. It doesn't matter on which side you write it. And then you use the boundary conditions given in the question to find the integration constant. So that's the separable differential equation. Next, we can look at homogeneous differential equations. So basically what you've got to do here is substitute another variable, say v, in for f of y over x. A homogeneous differential equation always has f of y over x, so that means you have to substitute v equals y over x, so we have dy by dx equals f of v. And then you use implicit differentiation. So when, for instance, if you're trying to differentiate xy, you can't differentiate that directly, so you have to differentiate it implicitly. And you do this exact same thing here to sort of get it into the form of v plus x times dv by dx. So once you have that form, you can just solve the differential equation like you would a separable differential equation, and you get a solution with respect to v and to x, and you substitute back in order to find the solution in terms of y, because right now we have it in terms of v, so we undo this substitution in order to find it in terms of y. Now here's a third way to solve differential equations. So there's something known as an integrating factor, and the integrating factor, when we have an equation which is like dy by dx equals p of x times y plus p of x times y equals q of x, then the integrating factor is actually the coefficient function of y, and that's the, so what we do here is raise e, so that's 2.72, or so Euler's number, right? Approximately 2.72, and we raise that to the integral of a p of x, so the coefficient function of y, with respect to x. So our integrating factor is just e to the integral of p of x dx. And so first, when you have an equation in this form, what you've got to do is to find the integrating factor. So once you have the integrating factor in this sort of form, you can multiply both sides by the integrating factor. So this is just dy by dx, and we've multiplied that by here, by this integrating factor. So I've just split the y from the d over dx operator. So what this is basically the e to the power of the integral of p of x with respect to x times dy by dx, and we have that's equal to q of x times the exact same thing. So now that we have this sort of thing, we can get rid of this derivative by integrating both sides with respect to x and solving this equation for y like we would. So this left side sort of simplifies here, and then the right side is what we are trying to find. So that's the integrating factor. So now let's take a look at an exam practice question. This topic is a little bit difficult, and the only way to get good at it is by using practice questions and past paper questions. So this is a past paper question. So have a go at it, and I'll walk you through the solution very quickly. Okay, so now that you've hopefully had a chance, we'll look at the solution. So the first thing to do when you have Euler's method, if we go back to that slide, is write down recursive equations in this form. So here I've just skipped writing down the xn plus 1, but basically if you know that step size is 0.1, then xn plus 1 is just equal to x of n plus 0.1. So as you can see in this table, it's 1, 1.1, 1.2, 1.3, so that's quite a simple equation, so there's no need to write it down. But if you really wanted to, you could write xn plus 1 equals xn plus 0.1. Now, the next thing we've got to do is do yn plus 1. So basically, yn plus 1 is, as we can see here, y plus h times f of x n comma yn. So here h is 0.1, it's given in the question, so yn plus 1 is yn xn minus 1. As you can see, that's what's given here by the question, and then times the step size times yn, which is what we needed to do to get it into this form. Now that we have this in this form, we go to the recursion function in our GDC and type in both equations. We also type in the fact that y equals 2 when x equals 1 by going into the setup function for the recursion function. And once we have that, we get this table here. And we're looking for the value of y when x is 1.5. So on this table, we've got to read at x equals 1.5. So we get y equals 2.87603, which basically means that to three significant figures, y is 2.88. So yeah, that's how you would solve a question like this. Please do let me know down in the comments below if you have any questions regarding this topic. I know it can be quite a tricky topic, so don't hesitate to ask any questions or doubts you have. And I hope you found this video helpful, and yeah, thanks for watching.